Let's talk about slope fields or direction fields. For example, graph some solution curves for the differential equation dy dx equals 0.5y. What's amazing about slope fields, or sometimes we call them direction fields, is that you can actually graph solutions to this differential equation without solving the differential equation. We can do it without actually finding a function y that satisfies the differential equation. Here's how we do it. Suppose the solution curve passes through 0, 1. What can we say about the curve? It has slope 1/2 at this point. Why? Because notice, we're being told that the derivative of this function, whatever it looks like, the derivative, is 0.5y. At the point 0, 1, y is 1, so that means 0.5y is going to be 0.5 times 1, in other words, 0.5. So even though we have no idea what the solution is going to look like, we know that at the point 0, 1, it's going to have slope 1/2. In fact, notice that there's no x in here, so whenever y is 1, the derivative is going to be 1/2. So the same thing's going to be true if the curve, if the curve passes through 1, 1, 2, 1, 3, 1, etc. At all of those points, the derivative is going to be 0.5. And again, we have no idea what the curve looks like. But we can do this. Okay, so we have, let's see, we have 0, 1, it has slope 1/2. That'd be about like that. At 1, 1, it has slope 1/2. At 2, 1, it has slope 1/2. At 3, 1, it has slope 1/2. So at all these points, whenever the y-coordinate is 1, it's going to have slope 1/2. Okay, now let's do the same for y equals 2, y equals 3, y equals -1, y equals -2. Okay, so when y equals 2, if we just randomly pick a point where y equals 2, like let's say, I don't know, let's say 4, 2, for example. I'm just making that up. Okay, since y is 2, we know the derivative is going to be 0.5y. In other words, 0.5 times 2, or 1. So at this point, the derivative is going to be 1. In fact, the derivative is going to be 1 at all of the points where y is 2. So for all of these, the derivative, dy dx, is going to be, it's going to be half y. Here, that's going to be 1. When y is 3, that's going to be 1.5. When y is -1, whenever, for any point where y is -1, the derivative is going to be 0.5 times -1. In other words, -0.5. And whenever y is -2, the derivative is going to be 0.5 times -2. In other words, -1. So let's go ahead and graph those points. Okay, so again, we start off with these. Wherever y is 1, the slope is going to be 1/2. So let's do that. So whenever y is 1, the slope is 1/2. Kind of sloppy, sorry about that. Okay, and then whenever y is 2, the slope's going to be 1. So here y is 2, let's graph little lines with slope 1. Okay, and then when y is 3, the slope is 1.5. Well, that 3 is off the charts. We're off the hook here. Okay, when y is -1, the slope is -1/2. -1. Okay, so we need something with slope -1/2. Something like that. And then lastly, when y is -2, the slope's going to be -1. So when y is -2, it's going to have slope -1. So let's do that. Okay. We can sketch rough graphs of the solutions. Set of line segments. Okay, so this set of line segments that I've just graphed, it's called a slope field or direction field. Right now, it seems like no big deal. Why are we learning this at all? But the cool thing is that we can sketch rough graphs of the solutions. Let me show you how we do that. First of all, let's change colors. Can we change colors? Yeah, here we are. Let's change, I don't know, let's change to blue. Okay, so if it goes through this point, it's going to have this slope. But as it goes higher, it's going to have a higher slope. So we're going to end up with curves that look like this. Okay, and in the same way, if it goes through this point, it's going to have this slope, but as it goes further down, the slope will get steeper down, and we'll end up with something like this. Okay, now there's a cool one that I didn't do. How about y equals 0? I want you to think about this for a moment. If y is 0, what's the slope there? What's the slope of that little line going to be? You're right. The slope is going to be 0 because the slope is 0.5 times y. In other words, 0.5 times 0, or just plain 0. So, switching back to the red here, we need to graph line segments with slope 0 when y is 0. Okay, and so now we can get a better sense of what these slope fields are going to look like. So yeah, it's going to be more like this, more like this, more like this. Now I'm going to be honest with you. You would really have to graph quite a few points in order to get ones that look like this. So you may be thinking, where does this guy get these from? Okay, if you had all the patience in the world, all the time in the world, and you graph lots of points, you'd end up with something that looks like this. But there's a better option. There are online slope field generators. To graph them, you just Google or enter into your favorite search engine, direction field generator or direction field plotter or slope field generator or slope field plotter. I shouldn't say Google. I should say enter that into your search engine. Here's one that I like, but there are others that are like that too. Okay, so here's the online slope field generator. Oh my goodness. This is what I came up with. And this is what we have. Look at that. The online slope field generator is so much better. Be careful when you use these plotters. 2 times y plus x must be written as 2 times y plus x. So if you click on the plotter, oh, this is so cool. Okay, so this is the slope field. But this is what you get if you plot the solution curves. You just click on these points and you get solution curves. It is very cool. Now let's suppose we drop an object. And again, you can play with this on your own. Let's say we drop an object. Let v be the velocity of the falling object. The acceleration due to gravity is negative 9.8 meters per second per second. Let's find a differential equation involving v. Our differential equation is dv dt equals negative 9.8. Why? Because acceleration is dv dt. So if I say the acceleration is negative 9.8, you could express that as a differential equation, dv dt equals negative 9.8. We're told that initial velocity is 0, so the initial value is v of 0 equals 0. So this is an initial value problem. Okay, so that's our differential equation involving v. If I were to ask you to graph the slope field and plot the solution to the point 0, 0, here's what you'd end up with. Okay, dv dt equals negative 9.8 and v of 0 equals 0. This is what we get. Okay, if you just graph dv dt, again, they're not going to have a dv dt, you're just going to do dy dt, but you're smart enough to, to replace the v with the y. This is what you get. Now, to be honest, we didn't need to use the online plotter to do this because we can figure out what the solution is. We can see what the solution to this is going to be. The derivative of v with respect to t is negative 9.8. So you just take the antiderivative and you end up with v equals negative 9.8t. So the velocity is going to equal negative 9.8 times the time elapsed. And indeed, that's what this curve looks like. It just looks like the line y equals negative 9.8t, and it goes to the point 0, 0. So to be honest, we didn't need a slope field generator for that. We could have done that on our own. Again, what this shows us is the velocity of a falling object if it's been falling for this many seconds. So these are the seconds, and these are the meters. This is cooler, though. Now let's take into account air resistance. It turns out that the force of air resistance is directly proportional to the square of the velocity. So not will we have that? Yes, we will have that. So we're going to have dv dt equals negative 9.8 plus kv squared. Okay, this is what we had originally, but now we need to take into account air resistance. Air resistance is proportional to the square of the velocity. And it's going to be dv dt equals negative 9.8 plus kv squared, because air resistance is hindering velocity. It's making it less negative. See, dv dt is negative, and then this factor, the air resistance, is going to slow it down. It's going to make it less negative, so you would add kv squared. Okay, so for example, for a skydiver falling spread eagle without a parachute, sounds painful, the constant k equals 0.0032, and you can confirm this through the experimentation. Graph dv dt equals negative 9.8 plus 0.0032 v squared with initial value v of 0 equals 0. This would take you forever if you did it just on your own without a slope field generator. But if you've got a slope field generator, bam, you can do it like this. This is very cool. So that's what the graph's going to look like. Notice, this is totally different from the other graph. From the other graph, without air resistance, this skydiver goes faster, 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 faster. Here, the skydiver doesn't go faster, faster, faster. Okay, initially faster, faster, but eventually the velocity levels off. And that's what we call terminal velocity. So estimate the terminal velocity. Well, it looks like I'd say it's about negative 55 meters per second, or about negative 120 miles per hour. To be honest, we usually express it positively, so 55 meters per second, 120 miles per hour. There are people who have survived falls without a parachute, but it's usually because they fall into trees or into a snowbank or something like that. Ordinarily, if you hit the ground at 120 miles an hour, you're not going to make it.